We will now go on to a very important basic concept in the study of dynamics, of motion in general, and it's got to do with what are called conservative forces. And we will introduce the very, very important concept of a potential associated with such forces. So as always, let's begin with an extremely simple observation, and that's the following. We know that if you have a particle or a body of some mass m at some position vector r, and a force acts on it and displaces this object to a neighboring point, let's say r plus dr, and some kind of force acts on it and displaces it by this infinitesimal amount, then the work done on the particle or the body let's call it dw, this is equal to F dotted with dr. In other words, that component of the force which is along the direction of the displacement does the work, and it's equal to dw, and this amount is given by the scalar product of F with dr. So this immediately suggests, well, for one thing, it says that in Cartesian coordinates, for instance, you could write this as fx dx plus fy dy plus fz dz, remembering that dr in general can be decomposed along ex, ey and ez, and similarly for f. So this suggests immediately that each component fx, fy, fz is some kind of derivative of this infinitesimal amount of this work with respect to the corresponding displacement. For instance, suppose you did not have any displacement in the y and z directions, then dw over dx would be equal to f sub x. So we have this idea that somehow or the other the force and the work it does on a body are related to each other by this rule of differentiation. You differentiate this quantity and you end up with the component of the force. More generally, where does this force go? Where does this work go? It goes into the stored energy of the system. To give an example, a very simple example, suppose here is a ground level and I have a mass m sitting here, and we have a shelf at some height h above the ground, and I lift this mass up and put it up here. I have done work against the gravitational field of the earth in lifting this mass up and putting it up at a height h, a certain amount of height, a certain height h, and if I started at rest here and it's at rest here at this point, then it's clear that some kind of stored energy of this particle has increased by a certain fixed amount. In this case we know the answer, it's mgh, and this means that that mgh is stored as energy in this system, and we say that the potential energy of this object in this case is equal to mgh. And the reason for the word potential is that if I were to drop this object when it attains the ground level, it's this energy, this amount of energy gets converted into kinetic energy, and this object hits the ground with a certain impact. So that's the reason for this word potential energy, but already you can see that the idea that an object can store energy in a form other than its kinetic energy is implicit in this very, very simple example. Now what the concept of a potential and conservative force is going to do is to make this much more general, as we will see, and we will do this by a sequence of examples of various kinds. Taking this example itself to start with, what it implies is that if you have the ground level and I say that the potential energy at this point is 0, on the other hand at a height z, let's put the z coordinate in the vertical direction, above the ground level, the potential energy Pe equal to mgz, then there is a relation between the force acting on the body here and this potential energy in the following sense. You can see that the force acting on the body is downwards like this, and it's equal to minus g times the unit vector in the z direction, minus because it's acting downwards here. it immediately suggests that the relation between these two is that if I call this V of Z, the potential energy at a height Z above the ground, taking the ground level potential energy to be 0, then it immediately follows that the force on this body F, when it is at a height Z above the ground, this is equal to minus dV over dZ times Ez. So V itself is mgz, so dV over dZ is mg, and you put a minus Ez and you have a force which is minus mg Ez in this fashion. So there is this fundamental relation which says the force is the minus the derivative of the potential, or potential energy in this case, with an appropriate unit vector to give the direction. Now of course you could put different masses at the same height. So you would like to have a concept which is related to the gravitational force alone without bringing in the specific mass. If I put in some other mass, capital M, then again this would be minus capital mg Ez. So I could define not a potential energy but a potential, gravitational potential, because it's the gravitational force, potential at height z equal to say phi of z, and this is equal to, in this problem this is equal to g times z itself. So you could look at the potential in this sense as the potential energy per unit mass in this case. So you multiply it by the mass and you get the actual potential energy of the object, and the force of gravity on that object would be minus dV over dz. The force of gravity on any object would be m times the derivative of phi of z. So force equal to mass, let me call it test mass to see. Whatever be the mass that you put at this point, multiplied by minus d phi over dz times Ez. This fashion. Now what's the use of this concept of potential? We will see this in a minute after we look at a few more examples, when we can see that in each of these cases it will turn out that the force, corresponding force, will always be a suitable derivative of some kind of a certain potential, or if you give a general object with some specific mass or charge or something like that, it will be that quantity multiplied by the potential, and it will turn out to have the physical meaning of a potential energy of this object. Let us look at a second example here immediately. Suppose you have, and this is a very familiar example in electrostatics, suppose you have an infinite uniformly charged plane. So the xy plane is uniformly charged plane with a surface charge density equal to sigma, say. So sigma is the amount of charge per unit area of this infinite xy plane. And then at a height, so let us draw some coordinate system. So that is the xy plane, that's x, that's y, infinite plane. So the plane is of infinite extent in the xy directions, and now at any arbitrary height, anywhere for that matter, it does not matter where you choose the origin on this plane, at any height z above the plane, at this point z, height z above the plane, we can find out what the electric field looks like. The electric field, as we know, if you put a test charge here, a positive test charge, and sigma is positive, will be perpendicular, will be normal to this xy plane, it will be directed upwards, and it will have a magnitude E. Well, the vector itself E at a height z will be equal to sigma over 2 epsilon naught, where epsilon naught is the permittivity of the vacuum, multiplied by the unit vectors Ez in this fashion. That's E of z. And the question is, can I relate this E of z to some potential such that the derivative of that potential with an appropriate minus sign is going to give me this force? And the answer is yes, immediately, because this will correspond to a potential phi, which will be a function of z, of course, equal to minus sigma z over 2 epsilon naught. And this will be that E of z equal to minus d phi over dz times Ez. The minus signs will cancel out and give me this force here. So this means in this particular problem, where the force is actually a constant independent of the height above the xy plane, because it's an infinite plane in this direction. In this problem, it so happens once again, like in the problem of gravitational field there, the potential is linear in the coordinate, depends on a single coordinate. There is no dependence on x and y, because this thing is uniform and infinite in extent, uniformly charged, and therefore this potential does not depend on where you are as far as the x and y coordinates are concerned, only depends on how far you are above this plane or below the plane. We will come to that in a minute. Okay. So such a potential, a linear potential, if you differentiate it once, will give you a constant force, exactly as in that case here. There is a slight difference here, because you could potentially go down, you could also go down below the plane, and then if you put a unit test charge, positive test charge here, and sigma is positive, the force would go in the opposite direction. So what do you think the potential is going to be for z less than 0, namely below the xy plane? Well, the answer is easy once again to guess. In this case, phi of z would be equal to sigma z over 2 epsilon naught. So this is for z greater than 0, z less than 0, because now if you differentiate it and write down minus d phi over dz, this would imply therefore that minus d phi over dz is equal to minus sigma over 2 epsilon naught. And if you multiply this by Ez, goes here, which is indeed the direction in which the force acts on unit positive test charge here. So this again tells you that you can combine both these quantities, and this is equal to the electric field at a point z for z less than 0 here. So you could combine both these things and say the potential, the electrostatic potential due to an infinite uniformly charged plane with charge density sigma sitting on the xy plane, this electrostatic potential phi of z must be equal to what we have here, minus sigma over 2 epsilon naught, the modulus of z. Mod z is minus z in the case of z less than 0, so it gives you a plus sign here and you have a minus sign here. Okay. From this it follows, this implies that the electric field E of z equal to you need to differentiate it with a minus sign, so this is equal to whatever derivative we had, minus d phi over dz Ez. Remembering that because the field or the force points upwards above the z axis, above the xy plane, and below, downwards below the xy plane, it's clear that the force changes direction as you go from above to below the plane, and therefore the potential is discontinuous as far as its derivative is concerned, because the derivative gives the field here. And indeed you see that discontinuity coming from the fact that this potential is a function of the modulus of z, which as you know is a V-shaped curve. If you plot mod z versus z, it's 45-degree line for z positive, 135-degree line for z negative, with a sharp point at z equal to 0. So as far as that is concerned, we have a simple expression for the potential, and we can derive the field from this potential. Now the potential energy itself would depend on, or the force on the particle itself rather, would depend on the test charge that you put. So if you put a charge q, you know that the force on the charge is q times E. So once you have the field, finding the force itself only is a multiplication, a question of multiplication by a certain constant. Now let's look at a less trivial example than this. Let's look at what happens if you have a gravitational force due to a spherical body such as the Earth, and we ask, given this Earth with some radius capital R, this is the Earth, and I ask what's the gravitational field at a point here. Now this is a spherically symmetrical mass distribution. We have assumed the Earth to be a perfect sphere. For such a situation, Newton's law of gravitation turns out to yield a gravitational force here which is directed towards the center of the Earth from the point concerned. It does not depend on where you are as far as the latitude or longitude is concerned. So it doesn't matter what the angular coordinates are. At all points at a given distance little r from the center of the Earth, the gravitational force is the same in magnitude and acts always towards the center of the Earth, towards the center of this mass distribution. So the force at this point acts inwards this way, and the force at that point acts inwards this way, and therefore we could write this force at a distance r from the origin. So if this distance is r, this is equal to minus g times m, let's call this the mass of the Earth, times little m, that's my test mass, whatever mass I put at this point, like the test charge, divided by r squared times the unit vector in the radial direction, with a minus sign to show that the force is directed radially inwards as opposed to outwards. So that's the force, and this we know from Newton's law of gravitation, together with the fact that this is the gravitational force on this point due to every mass element of the Earth. And the remarkable thing which was discovered by Newton first is that when you have a spherically symmetrical mass distribution, then the field at any point outside does not depend on the angular coordinates of that point with respect to this origin, but only on the radial distance from this point. So this magic property of spherically symmetric mass distributions is common also to the case of the Coulomb potential, or the Coulomb electrostatic force between charges. There too, if you have a spherically symmetrical charge distribution, we will see that the potential at any external point is dependent only on the radial distance from the center of this charge distribution to the point concerned, and not on the angular coordinates. That's the reason I've written r here rather than write r comma theta comma phi. I haven't put those in, no angular coordinates, only the radial coordinate has been put here without a vector symbol to show that it's only dependent on the radial distance. So this is the magnitude of the force without the minus sign, and that's the direction. Minus ER is the direction here. So the question is, can I write down what the potential energy of this object is? In other words, is there a function V of r such that f of r is equal to minus dV over dr, V of r, times E sub r? Can we find such a V of r? And inspection shows you that you can, because you can immediately see that if I choose V of r equal to minus g m m over r and nothing else, then if I differentiate this quantity, because I have a 1 over r, the derivative is minus r squared. So there's a minus sign coming from there, and there's already a minus sign here, so that gives me a plus sign, but I have to find minus dV over dr. That puts the minus sign back once again, and I multiply it by ER, and I get the gravitational force here. So that's the potential, and it's in fact the potential energy of a test mass of equal to little m at a distance r from the center of the Earth. This is the capital M, the mass m here. So exactly as in the electrostatic case, I can define a gravitational potential. So gravitational potential due to the earth at a point distant r from its center for r greater than or equal to r. We need to have the force due to the entire distribution, the full mass of the earth. This quantity is phi of r. It's a function only of r, not of theta and the azimuthal angle phi, the latitude and longitude, and this quantity is equal to minus gm over r. This quantity. So it's a function only of the radial distance. Once again, I differentiate this quantity, I get a plus gm over r squared, I take minus the derivative, and I get minus gm over r squared, and I multiply it by the mass to give me the force on a given mass little m, and multiply by er, and I get this gravitational field here. Now what does this thing look like? If I plot this function, it says if I plot little r here, 0, and this is phi of r, this looks like, we don't know what's going on till you hit capital R. This formula is only true for little r greater than capital R, greater than equal to capital R, namely from the surface of the earth upwards into space. Something else happens inside here, we will come to that subsequently later on, but the graph as far as this is concerned starts at some finite point minus gm over r and goes like that. So this quantity here, g capital M over capital R, is what we are used to calling as little g, as you know, and with an appropriate sign it says things fall downwards to the ground. Okay. So this again tells you that the effect of this force, which is a vector after all, can actually, the force itself can be expressed as a suitable derivative of a scalar function called the potential in this case. And this is an extremely useful idea. The fact that you have a scalar function which you can which gives you all the information that's actually contained in the force itself. Now you might have one very important question, which is the following. After all, if you have the derivative of this function equal to this force, and this is what is physically measurable, you could always say then that if I add a constant to this potential, it doesn't get differentiated at all. The constant's derivative is 0, and therefore the force, the physical force, will not change. Does that not mean that the potential in every case is determined only up to an additive constant, which is completely arbitrary because it will not show up when you differentiate it to get the force? And the answer is yes. You always, when you specify have a potential here, have to specify a reference level with respect to which you're measuring this potential, or you're computing this potential. In the case of the example, the normal example of the ground being 0 potential, this you say z equal to 0 implies phi equal to 0. With respect to the ground level taken to be 0, the gravitational potential at any point at a height z above the ground is g times z, okay, with respect to that 0. In this problem, the reference level is taken to be 0 at infinity. In other words, when an object is infinitely far away from the Earth's center, the gravitational potential at that point is taken to be 0, and with respect to that 0, the gravitational potential at any finite distance r is minus g capital M over r. So this is important to remember, that in every case we will always implicitly or otherwise have a reference level for the potential or potential energy with respect to which we compute or write down expressions for these quantities. This is an important point. And this reference level is chosen at your convenience. So as you can see, even from these simple examples, in some problems it may be convenient to choose it at some finite point, such as the ground, to be 0 potential. On the other hand, in other cases it might be convenient to choose it at infinity on physical ground, saying that infinitely far away there's no force, gravitational force is vanishingly small, and I choose the potential there to be 0. Okay. Now, can we generalize these things a little more? And the answer is again yes. How is it that I was able to do this calculation in terms of r without bringing in the other coordinates? After all, when we started with the statement that that the work done dW was equal to F dot dr, and if I write this in Cartesians, it's Fx dx plus Fy dy plus Fz dz. In general, there are three independent coordinates x, y, z, or if I were to write this in terms of spherical polar coordinates, for instance, this would be equal to Fr dr plus F theta d theta plus F phi d phi with appropriate dimensions for Fr, F theta and F phi, remembering that this quantity here does not have dimensions. This thing here has dimensions of length, and this therefore dimensions really of a force, but these quantities, these are dimensionless quantities, so these components will already have force times length as physical dimensions in them, and that's got to be remembered. So how is it that I was able to get away with the fact that only this dependence came in? And the answer arose in these examples. The answer comes from the fact that I know already that the force is radially inwards or radially outwards, and such forces are called central forces, forces which in spherical polar coordinates do not depend on the angular coordinates but only the radial coordinate. They are called central forces. If the force is directed only radially, it's called a central force. We will come across, we'll elaborate on this concept a little more as we go along, but that's what enabled me to, so to speak, invert this expression, because the other two terms in some sense were not present at all. When they are present, you need a little more general way of writing this derivative, and it involves what's called the gradient operator, which I will not go into at this stage, but we will come across examples where you need that. But we'll see why the central force is a very important concept and why it appears so often.